Hi there, everybody. We are going to be talking about how electron configurations can be determined directly from the periodic table, not drawing orbital diagrams and not looking at that diagonal chart, but directly from the periodic table, from patterns of electron configurations on the periodic table. This is exactly what you guys did in your lab on Wednesday, and the conclusions that I was hoping that you would be able to draw on your own, because then it becomes really yours. But I do want to summarize them here so that you can see how electron configurations work. So we're going to do a couple of practice here, and I'm going to use the periodic table I've put on the screen here, which is color-coded in a very specific way. And let's just go ahead and get started. So what we really need to realize is that when I say there's patterns on the periodic table, we're talking about the very last orbital that electrons are placed into. For instance, let's take boron. If you think about boron, and let me get a pen here. If you think about boron, boron's on the periodic table right here. It has 5 electrons. So when we talk about 5 electrons, those 5 electrons, the first 2 would go in the 1s orbital. The second 2 would go in the 2s orbital. And then the last one of the 5 would go in a 2p orbital. So when I say there's patterns on the periodic table, we're really focusing on this very last orbital and how many electrons are in that orbital. Where are those electrons going, and how does the position on the periodic table seem to fit in with that? Notice that boron ends in P1, and specifically 2p1. So notice it's in the first column of this big yellow block over here. And so every element, if you did aluminum, gallium, indium, thallium, any of the elements in this, they would all end in P1, every single one of them, meaning that there's 1 electron in a p orbital. If we went on and did carbon, carbon has 6 valence electrons, 1s with 2 electrons, 2s with 2 electrons, and then in the 2p orbital, there would be 2 electrons for a total of 6 total electrons. But again, we're focusing on this very last orbital, and you can see that there are 2 electrons in there, which means carbon ends in P2. The orbitals before the p orbital are all full, but the p has 2 electrons in it. Now, I hope you see that this one first column was P1, the second column was P2, and that you can start predicting that this column probably would end in P3, this column would end in P4, group 17 would end in P5, and group 18 would end in P6. And I can't seem to write up there, so you're going to just have to go with me that that would be P6. I don't know why it's not writing up there. So anyway, P6. Okay, so P1 through P6. That's one of the patterns you should have recognized. We can also recognize the same type of pattern over here on these first 2 groups, the alkali metals and the alkaline earth metals. So let's just take a look at those real quickly. I'm going to erase what I've done so far. And let's go ahead and write. Let's do lithium. If you look at lithium, lithium has 3 electrons. And so the first electrons would go in the 1s orbital, and the last electron would go in the 2s orbital. Again, we're focusing on this last orbital. How many electrons are in that orbital? 1. It's S1. So this column and every element below it and above it ends in S1. So that's a really important pattern. Now, if that's S1, following kind of what we saw over here, every element in the second column is going to end in S2. Now remember, s orbitals, there's only one type of s orbital. Once they have 2 electrons, they're completely full. And notice we have S1 and S2. There's no more column in this section over here because there's no such thing as S3. You can't have 3 electrons in an s orbital, and there's no more s orbitals on any energy level. So this block over here, this blue block, is often called the S block, groups 1 and groups 2. The S block, because every element in that block ends in an s orbital. So I bet you can figure out what this big yellow block is called, because every element ends in a p orbital. This is called a p block. Now, a special note, helium. Helium does not have p orbitals because it's on the first energy level. So it doesn't have any p orbitals. So a lot of times helium is not written here on the periodic table, even though it behaves like all these elements below it in the noble gases. Sometimes helium is written over here in this section because really helium ends in S2, and it belongs more in here when we talk about electron configurations. We'll get to why it's over here later in the next unit, but for electron configurations, it ends in S2, so often it's written over here on the S block. So if that's the S block with 2 columns, and this is the P block with 6 columns because 6 electrons fill up the 3 p orbitals, what do you think this big red block is called? And let's count how many columns are in it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 columns, that would mean 10 electrons. That would need 5 orbitals. What type of orbitals have 5 different types? Hopefully you said the d orbitals. And indeed, this is the d block. The d block has every element ending in a d electron when it comes to electron configurations. This would be d1. Every element in this column ends with 1 electron in the d orbitals. Then d2, d3, d4, and I'm sure you can see the pattern here, d5, d6, d7, d8, d9, and d10. So that's the d block. Now we have one type of orbital left. It's the f orbital, and we're not going to really focus on f orbitals, but I'm going to show it to you. The f block is way down at the bottom here. These are called the inner transition metals, and they make up the f block. And how many different f orbitals were there? 7 f orbitals. 7 f orbitals. So 7 f orbitals can hold 14 electrons. How many columns do you think are in the f block? If you count across, there are indeed 14 columns in the f block, because there's 14 electrons that can fill up those orbitals. We are just going to focus on the s, p, and d blocks because that is where we're going to be using elements most often. We won't get down to the f block very often. So let's next think about energy levels. Energy levels correspond to periods. So period 1 would be the first energy level, meaning 1 s orbitals. Notice on the first energy level, there's nothing in the p block because there are no p orbitals in the first energy level. Then look at the second energy level here. Second energy level here. Sorry about the intercom. So we have this s orbital. Goodness gracious. Intercoms. Okay. So we have the second energy level. And notice on the second energy level, we have an s orbital and we have a p orbital because the second energy level has s orbitals and p orbitals. No d orbitals. Now this is where there's one trick, and that is the third energy level. Notice that the third energy level, we have s orbitals right here. We have p orbitals, we have p, but it doesn't look like we have any d's. Now this is the trick. Remember that diagonal chart? We learned that you fill up the 4s orbital before you fill up the 3d orbital. And so let's look on the periodic table. Here's the 4s block, so 4s orbital. What comes after 4s on your diagonal chart? 3d. The d block is actually shifted down 1. In other words, the 3d orbital you think would be right here, but it comes after 4s. So the 3d orbitals are actually 1 level down. Excuse me. So we have 4s, 3d, and then 4p. That's the only trick that doesn't quite fit perfectly with the patterns, but everything else does fit really nicely. So let's try applying this real quick and seeing how it works. All right. So let's take an element. Let's take sulfur. And I need a pen. We're going to predict what sulfur's last orbital will be based on its location on the periodic table. So notice it's right here in the 4th column of the p block. That means it's going to end in p4. So for sulfur, the last orbital is going to end in p4. Now what number is going to go in front? Well, that's the energy level. What energy level is sulfur in? Well, what period is it in? So we go over here. Oh, it's in period 3. So sulfur is going to end in 3p4. 3p4. Now what about all the orbitals before it? They're all full. every single orbital before that is going to be completely full. So now we just go through the periodic table and think about what orbitals come before 3p. Well, the 1s orbital comes in, so we fill it up. How many electrons can go in the 1s orbital? 2. After the 2s orbital is the after the 1s orbital is the 2s orbital. So we're going to put 2s next, and how many electrons fill up 2s? 2. If we keep going across the periodic table, after 2s, we have the p block, and it's the second energy level, so 2p. So the 2p orbitals are going to be full. How many electrons can go in the 2p orbitals? 6. And if you forget, you can just count. 1, 2, 3, 4, 5, 6. So 2p, 6. After the 2p orbital, we come to the 3 energy level and the s block. So 3s comes next. And how many electrons fill up s orbitals? 2. So we have 2 electrons, two columns, 2 electrons, we put a 2. And now, after the 3s orbital, we're in the block where sulfur is, the 3p orbitals, and we're over 1, 2, 3, 4, which is why we put the 4 here. So that's the orbital diagram, the electron configuration for sulfur, just by looking at its position on the periodic table. We didn't have to use the diagonal chart. We didn't have to use anything else. We just followed the order on the periodic table to get that. So hopefully that made sense to you. Let's try another one and see if it makes sense to you. We'll try a slightly harder one. I'm going to erase F block. Again, we're not going to get down there. Okay. For this one, let's do something in the D block. Let's do iron. So for iron, we have 26 electrons. And so we're going to have to put 26 electrons into orbitals. But again, we're not going to follow the chart anymore, the orbital diagram, or the diagonal chart I gave you. We're just going to follow the periodic table. So look at Fe's position on the periodic table. It's in the D block. And how many over is it in the D block? It's 1, 2, 3, 4, 5, 6. That means there are 6 electrons in the D block. So the iron is going to end in D6. Now, what's the number going to be in front of that? This is the one that was a little tricky. D block is just slightly off. It's in the 4th energy level, but remember, the D block is 1 less energy than the period. S and P are exactly as they match with the period, but the D block is 1 less. So it's in the 4th period. D is going to be 1 less than that. So it's going to be 3. 3D6. So iron is going to end in 3D6. If you drew out the orbital diagram for iron, you would see that it ends in 3D6. Now, what's all going to come before it? Every other orbital before the 3D orbitals. So again, we just follow the periodic table. First energy level, s orbitals. How many can go in an s orbital? 2. There's no p orbitals on the first energy level, so I go to the next one. We have the s orbitals on the second energy level. So I'm going to go ahead and write the 2s orbital, and we have 2 electrons that fill up the 2s orbital. So now it's completely full. What comes after 2s? 2p, second energy level, p orbitals. So I'm going to put 2p, and how many electrons fill up all the p orbitals? 6. And again, if you forget, just count. 6. So 2p6. What comes after 2p? 3s, right here, 3s. So I'm going to go ahead and write 3s. And how many electrons fill up the s orbitals? 2. What's next after 3s? We go across. 3p is after 3s. So we write 3p. 6 electrons fill up the p orbitals. After 3p, we're on the 4th energy level now. So s comes next, 4s. And how many electrons fill up s orbitals? 2. And now we're in the D block where iron is. So now we're at the 3D orbital that we expected, and we have 1, 2, 3, 4, 5, 6, which we had already predicted, 3D6. So that is the electron configuration for iron, just by using the periodic table. So I am going to erase that. I'm going to give you an example, and you should pause the video and try this one on your own. What do you think zirconium would be? What do you think zirconium would be? So I encourage you to pause here and try this one on your own. And then when you're ready, come back. And I'm going to do it very quickly. Okay, if you paused and tried it on your own, hopefully this is what you got. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and last but not least, 4d2. That would be the correct answer just by using the periodic table. If you have any questions about this, feel free to email me or ask me on Monday if you would like in a Zoom conference on during connections. But that is it. That's the whole thing of using the periodic table to predict electron configurations. I hope that helped you, and I look forward to seeing how you do on this. Good luck.